the last video I introduced you guys to static friction, which was the friction when the block isn't moving, but in this video I'll introduce you guys to kinetic friction, which is the friction that's involved when the block is moving. And with this example, now that we've got a slightly more in-depth understanding, I'll go into a slightly more challenging example where you've got a block. Let's say it's on an incline, so that vertical line there, or like slanted line, was actually just the slope of some mountain or something like that, and you've got a block resting on this incline, and let's say you've got some person, pushing this block. How do I want to do this? Yeah, how about this? We'll have one person pulling this block up the hill with a force P, and we're given that the block is actually moving up the hill, and the block also has a force due to gravity acting on it directly down, mg, and a normal force which is going to act perpendicular to the ground, n. Right? And let's say this block is moving uphill. Let's say this person pulling this block is successfully moving up the hill, albeit it's going to be tough, but let's say he is doing it. That means that there's going to be a kinetic friction force here, which is going to be given by, and we define it as mu k n. Right? So it's very similar to the static friction one, except mu k here has replaced mu s, and that's always going to be the case as long as the block is moving. So in this particular case, the block is moving up to the right, so there's going to be some acceleration towards the right. So I'll denote this as, I'll start an axis here, and I'll denote a as our net acceleration of our block as it's moving up the hill. And we're asked to find if we can just find some equation relating all these terms together to try and figure out what's actually happening on this block. So first of all, we can start off with creating an axis. So although we could, if we wanted to, create an axis like this one, let me just show you what I mean. We could create a standard xy axis where this will be y and this will be x. We could do that. That would be no problem. Although in this particular case, it would be much more convenient if we choose a slightly more suitable axis. We could choose, and I think you'll see why later on in this video, why this is a good choice, but this axis right here, where we denote this as x and this as y, would be a much more beneficial axis. There's just a whole lot less mathematics which you need to consider. And let's say this slant of this mountain, whatever it is at an angle of, I don't know, theta to the horizontal. Right? So this mountain is just angled at an angle theta from the horizontal. Well, we know that while this block is being dragged up this hill, the block is not going to fly up and down in the y direction, right? It's going to be stuck to this mountain, which means that the sum of forces in your y direction are going to be equal to 0. Right? Because the block isn't going to fly up or down while it's attached to this mountain. It's going to be dragged along it, right? So that means that n is going to be equal to whatever your component is of mg in the downwards direction. In fact, let me try and split that for you real quick. So we've got mg, and I'm just going to draw this vector mg down here real quick, mg, and that's going to be your hypotenuse of your triangle. But we can split that into its x and y components using simple trig, right? So that can be split into x and y coordinates using simple trig. And we know that it's got an angle of 30 to the horizontal, so we know this, sorry, not 30, we know it's got an angle theta from the horizontal, so we know that's going to be 30. This is a right angle, which means this is going to be 90 minus theta, which means that this, now viewing the whole triangle, is going to be equal to theta right here. So in other words, let me just redraw that a little bit better. That's going to look like this. That's going to be this. Theta is going to be here. This is just simple geometry. I kind of rushed through it. But this is going to be mg, and this is going to be theta, which means that the component of your force due to gravity is going to be, in the x direction, mg sine theta, and in the y direction, you're going to have a component in downwards of mg cos theta. Right? this implies that n is going to be equal to your downwards component, right? The upwards component is going to be equal to the downwards component, which is going to be mg cos theta. All right, so that's the vertical components done. That's going to be useful. We'll use this formula later on. But now let's consider the sum of forces in the x direction. Well, we know that because the block is moving, the sum of forces in the x direction is not 0. It's going to be equal to your net acceleration times by its mass. So this block is a mass m, and its net forces acting on it in the x direction are going to be equal to ma. Right? The block is not stationary, so ma is not going to be 0, right? And I've already told you to assume that the block's moving to the right, which implies that p minus, and all your terms acting to the left, or, well, down the slope, which is going to be minus mg sine theta, and minus, because mu k n is also acting downward down the slope, minus mu k n is going to be equal to ma. Notice how the left-hand side of this equation is the sum of forces acting in the x direction. P is acting to the right. These terms are acting to the left. That's why they're negative. Well, we can simplify this expression a little bit more by subbing in n and also dividing by m. So let me just simplify this equation I've just written here. And we can write a, your acceleration of your object, is going to be equal to p on m minus g sine theta minus mu k, and I'm just going to sub in n and divide by m, minus mu k g cos theta. Implying that your acceleration of your block up the hill is going to be equal to p on m minus g sine theta, sine theta plus mu k cos theta. Alright, so that's just this one particular example. In this one particular example, this will be this equation right here will denote your acceleration of your block up the hill. Notice how if mu k was higher, that would imply that the acceleration would be less, because this is times by a negative out here, right? Now this is given that our object is moving up the hill. In many questions you may not be given that type of information. In fact, what you need to do is you need to calculate whether the block's going to be up the hill or down the hill. And you do that by calculating the static friction coefficients first, and figuring out whether it satisfies the inequality I made above. I'll just scroll up so you can see that. So remember this, where we were talking about static friction. If the static friction equation doesn't hold, that means you can calculate whether it's going to be moving to the left or to the right. And if it's moving to the left or to the right, then you apply the kinetic friction formulas and then figure out how much it's accelerating by. In fact, I'll do an example just so you understand, but for now I just hope this makes sense to you. This basically describes how you can obtain motion if it's already moving and you know what direction it's moving in.